Section 8.6 is the last section in Chapter 8, and in this section we're going to be testing a claim about either standard deviation or variance. Now you may remember doing these types of problems back with confidence intervals, and with standard deviation or variance problems we weren't using a t-distribution or a normal distribution, and instead we were working with a chi-square distribution. This is the distribution that's skewed to the right, unlike the other two that are both unimodal and symmetric. So for this problem, it's giving us an alpha level of 0.05, sample size is 16, and it tells us that it's right-tailed. So to start off, we're going to go to 15 degrees of freedom, just n minus 1, and we're going to put all 5% on the right tail. Okay, and that's going to give us our critical value, 24.996. Okay, it also tells us up here, sigma squared equals 225. That's the variance, and that's what we're going to be working with here. We can write our hypotheses. So null hypothesis always has that equal sign. The alternative is based on this right here. It tells us it's a right-tailed test. So the last thing that it wants us to do here is show the critical and non-critical regions. Okay, so this is our critical value. When we actually plug everything in to the chi-square test statistic equation, which we're going to get to in a bit, anything larger than this value, since it's a right-tailed test, would be in the critical region, and we would reject the null hypothesis. Same thing for part B with two minor differences. So to start, it tells us that this is a two-tailed test instead of a right-tailed test, and it also says we're going to be working with standard deviation instead of variance, like in part A. So sample size of 12, 11 degrees of freedom. Okay, and since it's two-tailed, this alpha level is going to get split up where half is in each tail. So we have 2.5% on the right side, and then the other 2.5% on the left side. So there's two critical values here. Our hypotheses are a little different because this is the variance, and we want to run a test on the standard deviation. So we're going to say the standard deviation is just the square root of that variance. That's going to give us 15. Right? It's two-tailed, so our alternative is that it's not equal to 15. Critical regions, if we get a test statistic that's smaller than 3.816 or larger than 26.296, that would be the critical region where we reject the null hypothesis. If we're asked to find a p-value for these tests, it's the same process as when we were dealing with the t-distribution. So we have this test statistic, 29.321, sample size of 16, so we're going to go to 15 degrees of freedom. Right-tailed test, so we're on this side. Well, there's right side, this is the left side. So we're going to put this 29.321 on the table here. And if we did that, it's going to go in between those two. Okay, so it's larger than the 27.488, but smaller than that 30.578. So our p-value is somewhere in between those two numbers, somewhere in between 1% and 2.5%. Part B, we're going to do the same thing, 10 degrees of freedom, two-tailed, okay, which means, so let's go ahead and do this part first. 24.672 would go here. Okay, so it's in between 0.005 and 1%. However, this is just the right tail. Okay, I got a lot of stuff on the screen here, but basically we just found this. Okay, and since it's two-tailed, there's another section on the left side. So we're going to double this. Okay, this is what's on the right side. So we just do twice that, and this gives us our answer. If you can't see it, let me write it down here. So the p-value is in between 1% and 2%. It's twice whatever this one tail is. So that's all the setup of how to use the table. Let's do a problem start to finish. So in example 1, it's telling us the standard deviation of the pollution byproducts that we get when we burn a gallon of gas is 2.3 ounces. We take a sample of 20 automobiles. Okay, we test those, we get a standard deviation of 1.9. So is that going to lead us to a conclusion that this is actually incorrect, that is actually lower than the 2.3 ounces that we believe is true? We're using an alpha level of 1%. So null hypothesis is that the standard deviation actually is 2.3. Alternative is that it's less than 2.3. Critical values, alpha of 1%. We're doing a left-tailed test, which equates to that number there. We're on 19 degrees of freedom. because we have a sample size of 20. So our critical value is 7.633. For a test statistic, we're going to plug into this equation right here, n-1 times the standard deviation of the sample on the top divided by standard deviation of the population. That denominator comes from the null hypothesis. So we plug everything in and we get 12.966. That's our test statistic, just like we got z-scores or t-scores from the previous tests. Now we want to use that test statistic to find the p-value. So we're back to our chi-square distribution table. We're at 19 degrees of freedom, and we're going to put this value on that line. Okay? And if we were to put it on this line, it would go just to the right of this 11.651. So drawing out this curve, we got 12.966. Okay, if we actually got 11.651, that would mean that there was 90% of the distribution to the right. Chi-square distribution is always giving us area to the right, unlike the other two curves that give us area to the left. So since we got 12.966, it's a little bigger than this, means that there's less than 90%. Okay, this is going down, 99, 97, 95, etc. So over here, there's something that's a little less than 90%. Okay, let's just say for simplicity, it's 85. Okay, that's going to leave 15% over here. Okay, obviously that's just made up. What we can say is that the p-value is going to be larger than 10%. Okay, and that's because that 12.966 is larger than that number. Once you get to that, we're doing the same thing we've always done. That p-value is larger than the alpha level of 1%. It's larger than 5%, which is the standard alpha level. We're going to fail to reject because the p-value is too large. Conclusion, when we fail to reject, it's always insufficient evidence, and we're always writing this last sentence about the alternative hypothesis. There's insufficient evidence to suggest that the true standard deviation is something less than 2.3 ounces. Let's do one more start to finish. Here we have the manager of a large company who's interested in how long it takes to transfer a call. He believes the standard deviation is 1.2 minutes or less. Takes a sample of 15 calls. Based on that, we get a standard deviation of the sample for 1.8 minutes. At an alpha level of 0.05, we want to test the claim that the standard deviation is less than or equal to 1.2. Okay, we're going to use the traditional method for this one since we did the p-value method on the last one. So we'll start with this part, less than or equal to 1.2. Okay, we would write it like that. Sigma is less than or equal to 1.2. Now this has an equal sign, okay, which means that this is actually the null hypothesis. And if this is the null hypothesis, the alternative would be that sigma is greater than 1.2. Remember, the null hypothesis always has to have that equal sign. And since less than or equal includes a statement of equality, we can just write that as an equal sign and see, do we have evidence that that's actually incorrect? Critical value, based on this 5% up here, we're going to go to our table, 14 degrees of freedom. Okay, we're on the right side because it's a right-tailed test. We want to put on that 5%. So 5% on the right, 23.685. Test statistic, again, we're just going to plug it into this equation here. When we do that, we get 6.222. Reminder, our chi-square critical value is 23.685. And if we put all these on our curve here, here's our critical value. Anything that's larger than that would be reject the null hypothesis, and we got 6.222 out there. That is not in the shaded region, and because of that, we're going to fail to reject the null hypothesis. When we fail to reject, it's always insufficient evidence in support of this alternative hypothesis. So there's insufficient evidence to suggest that the true standard deviation is greater than 1.2 minutes.